Yes, so my name is Niklas from KTH. So the title is not for drone show, but this is no, it's my fault because I'm lazy. I'm recycling talks, but it's the same content. Basically, we want to present the work we had that was presented in Denver a couple of weeks ago as well, going into the scalable task triangle mounted with solid as well. So this work is it covers a extreme scale allocation of Lumi. So it's running a big simulation campaign in turbulent Rayleigh-Benard convection using a spectrum simulation as well. But before we go into the content, there's a lot of people on the authors list there, but just to give some credit where credit is due, it was a large team behind this effort that finally led up to this Golden Bell nomination. We didn't win, but it was very good work anyway. A big collaboration between various different European universities, and as you'll also see, a good usage of the EuroHPC resources as well. So we're looking into turbulent thermal convection, and you have applications that go from chip cooling down to heat convections in the Earth's mantles and the sun as well. So what we are studying is very canonical Rayleigh-Benard convection. So basically, you have your pipe, and you heat it at the bottom and cool it at the top. And then you start getting these convections going up and down in that tube. So it's not only a canonical test case, it also has this interesting question about the ultimate regime. Because as the Rayleigh number goes up very high, you might get some very strange scaling between the Nusselt and the Rayleigh number. The boundary layer might become turbulent. And this is a long-standing open issue that no one really has settled yet. Because we don't know if this can be done with experiments. Control experiment at this high Rayleigh number is very difficult to do, so the only way here is doing simulations. And of course, that means very detailed simulations. It has to be direct numerical simulations. So we have the large computational costs. We need very good numerics because we don't want to have spurious separations or triggers of these boundary layers, so that we don't have a false or claim that we have reached ultimate regime or not. So it has to be very good numerics. And the other problem is also that we have to run the simulation for a very long time. So it's long integrations time that we needed to get good statistics. And of course, big simulations produce unmanageable volumes of data as well. And that, of course, needs an efficient implementation. So just a quick side note on efficient implementation. So we talk about exascale a lot, and you can look at exascale in various ways. One way of looking at it is that you take a very large problem and inflate it even larger, and then fill an exascale machine. But what is more interesting for the CEEC project is that we try to improve our method so that we can take today's problem and just scale it out on larger machines. This is a more sober way of looking at exascale computing. And to illustrate that, I mean, back in the days I worked at Riken, we run full LES simulations of full car on the full machine. And that needed around 100 billion grid points. So K-computer, more than 500,000 cores, 10 petaflop, full room. That's now the power we have in the Kappa cabinet in our machine in the basement at KTH. So if you do this naive flop-to-flop comparison, you start to get a bit scary about what kind of problem sizes you need to fill the entire 309, this is an error now, is 380 petaflop Lumi as well. So that's going to be a very big problem, which is of course not feasible. So the solution here is, as most people know, and it has been known for a long time, you need to go to high order methods. They give you the nice numerical properties that we need for this work, but they're also very good, suitable for modern hardware like accelerators. But accelerators will give us a different problem. The problem is that if you look at the plot down to the right, there is a Bake-Off Kernel 5 benchmark program from SEED. And the red line is an AMD EPIC 7742 that will hover around 1 teraflop, and the x-axis is the problem size. So the AMD EPIC is just doing fine for any kind of problem size that we see, while the GPU, of course, is very happy if we have a lot of data. But that, of course, speaks against what I said in the beginning, because then we're going to need to have very inflated problem sizes to fill the machine. So for us, we want to scale out. So the challenge is actually to make the GPU fast down to the left there, where we have little amount of elements per device, and make it still being efficient. So just a quick note, it's late in the afternoon, so we should not go too much into numerics, but just saying that, I mean, KTH, we're doing spectral elements, so high order finite elements. Everything is matrix free, so we don't assemble the matrices, we don't assemble the element matrices either. Everything is a couple of fast tensor products. And what keeps continuity here is that we have gather scatter operations between various elements. And these gather scatter operations are compared to other high order methods. We only have unit depth communication stances, so it's very efficient as well. And this is building on all the work that went into NEC 5000 and Fry code before that. So we're building on good numerics that we know will scale. So based on that, at KTH and with collaborators, we have come up with a new portable spectral element framework called NECO. So it uses these key components of spectral elements, small, fast tensor products, and gather scatter operations. So how to make this portable is that we have made a new code in a modern object-oriented way. We're using Fortran 2008. We can take that battle outside if people want to do that. But the point is that we're building the solver based on these boxes that you see in the middle. So you have an abstract representation of the entire solver. The gray one are fixed. I mean, the mesh is the mesh. It cannot be changed. But the solver, the red pinkish boxes there, or the AX that we have down here, for example, that is represented as a virtual or abstract types in Fortran that comes with a deferred method compute, which of course is when you compute the action of A times X. And this has to be implemented on the actual hardware. So the solver itself will just work until this layer here. And all the green ones are the ones that are the actual implementation, depending on your hardware, for example, AX, CPU, SX, or GPU. And that will then be instantiated at runtime, given how you configure and build NECO as well. So this is the way we can support various hardware backends, going from CPU, GPUs down to more exotic vector processors and FPGAs. And for the accelerators, we have a device abstraction layer that we're going to talk about briefly as well. But when we just highlight the plot down to the right, it's NECO running on various machines in Europe. I don't expect you to be able to read it, but we can add some legends there. At the first, we have some CPU machines. In the middle, we have the SX Aurora machine in Stuttgart. And to the left is all the various GPU clusters at the time. So I'm not trying to show good scalability here, but rather say that all these different machines were running the same Fortran file for the scientists. So they don't have to sit and tune various things depending on the platform. NECO will just take care of that automatically. They just type up their problem in Fortran and then it's just compile and go. So good for them, but a bit more challenging for us. So we need to adhere to very good software engineering practices. So this has morphed into an exercise then in doing unit testing, verification, validation, and modern deployment using, for example, SPAC as well. So talk about the device abstraction layer, because now people need to go to accelerators. We had a big debate how to do this in a good way. We had some tries with directive-based approaches. We didn't see the performance that we liked, because it was, I mean, vendors are slow catching up on this. So the choice was to do native backends. So we actually have code for CUDA, HIP, OpenCL, and we are calling them via C interfaces in Fortran. So we are replicating everything that we need for example, HIP. And then we're calling that via the C bindings in Fortran as well. So all the device types that we have, they have a C pointer for possible allocation on the devices. And the way these kernels are invoked is that we have this wrapper function from Fortran that are then finally calling into the device code. And the device code is heavily templated with CUDA HIP or preprocessor macro OpenCL code, such that we can get the best performance out on various runtime parameters, for example, polynomial order. It also turns out that on the accelerators, it's not clear how, for example, the thread structure should look like for the best performance. So at any time, the first time we hit a kernel in the code, we run a separate runtime tuning based on polynomial order to find the best combination of threading strategy and implementations. And this is important because we are using multi-real, so we have various polynomial orders for each solve as well. One more thing, the gather scatter itself, key components for scaling. Here we have worked a lot when we tuned this for the vector card back in the days, was that we need to sort the degrees of freedom such that we have a lot of vectorizable injective neighbors. So basically this facet neighbors here that just have one neighbor, and then keep the green ones that can have multiple, the non-injective part low as possible. So everything is ordered and sorted such that you can do this injective part very fast with very long vector lengths as well. And this paid off because this was very good, of course, going to the GPU as well. But here we have some more challenges. So we have completely non-blocking MPI with using the device-aware MPI, and the graph in the middle shows really how much you gain from going from the host-based MPI on Lumi to device-based MPI. You can see there's a big difference in performance, and that's of course natural when you look at the node diagrams of the Lumi node. Another thing here that we have done is that everything is asynchronous, so the pack-unpack kernels are running in various streams depending on the neighbor. So for every MPI neighbor that we have a separate stream, such that we can pack, unpack, and we don't have to wait for the late arrival until we start with the unpacking process. But again, it's not clear which is the correct setting. That depends on your problem and the nodes that you get. So the first time you start up together scat, you run a set of auto or runtime tuning of all these combinations. So part of the solving can run fully asynchronous, some part of the solving might run synchronous, or a combination of both. So maybe synchronous pack and asynchronous. So these are sort of the interesting component going forward. So one more thing actually let's highlight quickly as well. As I said, we have a lot of data. So we actually are basing from a piggyback on a previous European project. So we have a lossy combined with lossless compression of data. So loss compression is actually keeping the most important modes of the solution. And that can then be passed down to a lossless compression, such that we can get down to 97% data reduction with a relative error of 2.5%. And if this is not good enough, you can always, there are knobs to tune there to get the tolerance that you need. The interesting here is how this is done in Echo itself. There's a diagram to the right. And the middle part, the hybrid compression, is the interesting one because then you actually run Echo, it's computing time steps. And then suddenly you then compute the lossy compression on the GPU. And then you stream this data to the CPU. But once the data is on the CPU, you can then continue doing time steps with Echo. And then the CPU, which otherwise doesn't do anything, can then do the lossless compression right to the disk. So we kind of overlap the I/O part of the code as well, which is very good when we have this large problem like the webinar. So all this combined, we were part of the LumiG pilot phase. And at the end of that, Pekka, the director of Lumi, he asked us, do we want to run on the full machine? And yes, of course, we want to try. So we set up this more than 100 million elements DNS case and got a time slot in the middle of the night. And so we ran the cases. So we did strong scaling here. So we used 20, 40, up to 80% of the full machine. And going through the data later on, you can actually see that this is close to 80% parallel efficiency towards here at the end of the scaling copy. And of course, this is very nice and very good. And most people will probably stop with this result, given the scale and that is strong scaling. But we got a bit annoyed about this gap here, so we wanted to try to close that one. And looking at the performance of our key kernels in terms of flops, we couldn't do much. So we went back to the numerics. So we should not go into too much detail here, but using an implicit explicit time stepping scheme. And for each time step, we are solving 3 velocity problems using coordinate gradient with block Jacobi. That's super fast. But then we have the pressure, GMRS with an additive overlapping Schwartz preconditioner. And this is, of course, the expensive part. And I mean, what has been devised earlier in the work of NEC is that you have a coarse grid, which is basically on linear elements. This is going to be the key component to get it scalable because you don't have much data. So reflect about it a bit. You actually go from a high order problem that is good for an accelerator, and then suddenly you are going down to a low order method, which is not enough to keep the GPU busy. So how we do this on both CPUs and GPUs is that we're using pipeline CG methods. which has a low maximum iteration limit that we just try to do, like, for example, 10 or 5 iterations and then we continue because it has deep down on the precondition. This scales even on the GPUs, but when we start doing profiling and looking at activities, so the top graph here is the GPU activity, and we can clearly see, not without even looking at the MTX host regions, we see that suddenly the performance goes down quite a lot. And this, of course, because the GPU is like a bucket of water, and with linear elements, we cannot keep this bucket full, so we cannot get full performance. So the way we addressed this was to look at this, and it's an additive preconditioner, which means that we have independent work. So the goal was to exploit this all available task parallels. So we launched the left and right part of this preconditioner in parallel on the device. And we do this from 2 different threads. So we create, once we have the application of this, we create a parallel region with 2 threads. And one thread is then injecting work into one stream and the other one in a different stream. So that we have separate streams to allow overlap between the different work and increase the GPU utilization. And then you need to play around a lot with the stream priority so that some of this is not actually starving the other, and you get into scheduling issues as well. But when you find the good values, you can see here that you actually have the core script solver at the bottom, and it's completely overlapped. This small amount of work here that was not keeping the GPU busy is actually now fully overlapped with the right part of the preconditioner, which is a fast serialization method that runs fast. And interesting here is also that we have all these orange boxes here is actually very fine-grained communication from the CG solver as well. And we also have some communication from the FDM part. So we actually have communication initiated from both of these streams possibly at the same time. So after having this, we were quite happy, and we wanted to try it. So we ran some experiments on Lumi in March, April this year, and on Leonardo in April. And it was very pre-production. We basically got access to Leonardo after we turned it on. But nevertheless, we ran the really binary case, 100 million elements, and a high value number of 10 to 15. So really where we tried to get to starting the simulation campaign to actually try to find a solution to the ultimate regime question. We ran on Lumi and Leonardo. If you're not aware, I mean, Lumi is AMD. It's this close to 400 petaflop, and Leonardo is a smaller one, but with NVIDIA 100. So we have 2 different platforms here with the same code base. And we're using 1 MPI rank per GCD on AMD and 1 rank per device on NVIDIA. And strong scalability, average time per time step is the field edited here as well. So finally, the plot itself. Now we actually have close to perfect parallel efficiency on both platforms. And that's nice and all, but the important thing is that we see that we have good parallel efficiency with less than 7,000 elements per logical GPU. And to put this into perspective, this is a significant reduction compared to what we had before. Before, the rule of thumb was 15,000 or 20,000 elements to keep the GPU busy. And that was what we used at the Lumi G hero round before, when we had 80% parallel efficiency. So now we can go down to 7,000, and this is mainly due to this new overlapped pressure precondition that we have as well. Just to mention, I mean, there are some confidence intervals here. These are 99% confidence intervals. For the computer scientists, I mean, there's an interesting spread on Lumi at scale. So who knows? Maybe some work can be done there, but it really is, the results are really actually accurate. That it's actually on spot on to the ideas and scaling for this one. So wrapping up a bit, the development work that led up to this submission is now supporting these runs to try to settle this debate about the ultimate regime. And what the direct output here is we have these in-situ data processing capabilities now that are crucial to run these large simulations. And we have this new task decomposed overlap pressure preconditioner that are really is the key ingredients to get this good scaling on both Lumi and Leonardo. And finally, it has been supported by both Swedish projects, CEEC, of course, and then some other European projects as well. And great support from UHPC, and specifically the machines and the people behind Leonardo and Lumi as well. That's it. Thanks a lot.
Thank you, Niklas. Perfect timing. Great. Good. Do we have any questions from Zoom or from audience?
Just one hand.
Yes, please.
Hi, so this is Uli again. I have two technical questions. So the one is, I see that you solved the pressure Poisson equation with GM-res. Shouldn't that be a symmetric positive definite system? Why then GM-res?
No, it's not, because we're doing some things with the boundary conditions, so it's not symmetric anymore, unfortunately. Yeah.
But if you had eliminated the boundary conditions, then it would become symmetric.
Yeah, but I don't remember the exact detail right now, but the matrix is not symmetric. So.
Yeah, which is typically that the boundary conditions are treated in an unfavorable way. That is of course true. But if you eliminated them, kind of pre-eliminated them, it should be symmetric positive definite. But anyway, okay. The other question is, you have shown impressive performance characteristics, but have you checked the convergence? Because if I'm kind of provocative, I would say if you did coarse grid solve and fine grid solve sequentially, you would get exactly the same performance if you do them in parallel.
I mean, convergence is...
So basically when you do them in parallel, one of them is kind of not doing anything. So they compute something, but it is not relevant for the convergence.
No, it's additive, right?
Yes,
so
but you're so from a multi-grid way of thinking, if you do not have the coarse grid correction, then computing the fine grid scales is irrelevant. So you're basically computing garbage, which doesn't help you in convergence.
So I mean, okay, but the parallelization is per level. So
yes,
yes,
but if computing, so the trick in multi-grid is that you alternate between fine and coarse scales. And yes, the fine grid scales can be improved if the coarse grid scales have been improved, and vice versa. If you do them in parallel, you're losing in convergence speed.
Yes. Yeah, okay, I see. What I forgot to mention is that we are actually just doing basically one level here. Because otherwise... So.
Yeah, but still, it would be interesting also to see kind of the speed of convergence if you gave up in doing coarse and fine in parallel.
A convergence
I would guess that if you always switch off half of the machine, you would see almost the same speed of convergence.
I mean, no, I mean, if you do it serial like we do here, so we have the normal, the right part first and then the left part. I mean, the performance is much lower because we cannot keep the GPU busy.
Yeah, that is the fundamental message of multigrid, that you have to keep the machine busy or have to keep the machine idle at some times to get the best possible performance. If you optimize for the performance, you're basically wasting energy and resources.
Yes.
Okay, so we can talk about that. Maybe this is not enough time, but that's kind of the core message of multigrid. If you try to work on coarse and fine in parallel, you're basically keeping your machine busy, but you're not helping convergence.
Yeah, I will be happy to talk about it. For sure.
Okay.
Yes.
Yeah.
Thank you, Uli. More questions? Otherwise, yeah, we are switching to the second speaker, who is Dinesh Parthasarathi from FAO, and he will be talking about optimizing multi-grid solvers using grammar-guided generic programming. Dinesh, the floor is yours.
Okay. Yeah, so I'm going to be speaking about multi-grid solvers and optimizing multi-grid solvers. So as you know, in like many simulation codes, you end up with having a large system of equations that needs to be solved efficiently. And one way to do that is multi-grid solvers. So they're asymptotically optimal methods. So designed carefully, they can be very efficient, at least for many PDs. So typically, you have these standard multi-grid cycles like V cycle, W cycle, or F cycle, and you have say some smoothing operations on each level. So what we want to do, or what we're interested in, is not just constrain ourselves to the standard cycle structures, but what we call as flexible multi-grid cycles, where we have the option to choose any flexible structure and not just conforming to the standard recursive structure of P and W cycle. And so not just that, so you can choose any arbitrary cycle structure. And as you can see, the nodes are colored. So the color represents a smoothing operation. So you can choose different smoothers at different points. And if you can see the node that is white, you basically can do no smoothing also. And you can also kind of select relaxation weights for each step. So this gives you a lot of flexibility, and the hope is that with so much flexibility, you can hopefully design a better solver than the standard multi-grid cycle. But it obviously has a very, very large search space, and it's kind of very difficult to do it by hand. So which is the reason why we use an optimization method. So we use genetic programming to kind of optimize the multi-grid solver over this large search space. So just a brief overview on GP. So you start with an initial population of, say, random programs, and you run these individual programs and evaluate their fitness. And then you perform these genetic operations like crossover and mutation, which gives you the next generation. And you basically, with each evolution of each generation, you basically get better programs with better fitness. And finally, when you do this iteratively, you end up with a final population where you have, say, valid, you have the best programs. So, but in our case, we are concerned with multi-grid solvers. So it is basically not useful if we just generate random programs. So we also basically want to constrain our population to valid multi-grid solvers. And for that, so we have this grammar-guided approach. So we impose grammar constraints to kind of constrain the program. So these basically are a set of grammar rules formulated for multi-grid solvers. So on the left, you can see production rules. So basically symbols corresponding to some expressions. So when you apply these rules iteratively, you end up with an expression that maps to a valid multi-grid solver instance. And basically, these rules are implemented in a framework that we have called Evo stencils, which optimizes multi-grid solvers. So these grammar rules are built into this framework, and we use the library called Deep for the evolutionary algorithms. So so basically, you have the Evo stencils framework, which basically uses these grammar expressions to evolve and basically perform these genetic operators. And then obviously to evaluate the fitness, which is the main thing. So it needs to be mapped to a solver framework. So until now, so we use, say, HypeWords for algebraic multigrid, or XStencils, which is the in-house code generation framework for geometric multigrid, to kind of evaluate each of these individual solvers. So we kind of have this step where we transform the grammar expressions to maybe a solver executable. And since we are doing a population-based method, so we can evaluate these individuals in parallel across, say, multiple nodes. And so once you evaluate the fitness, so this kind of guides the optimization process. So we are basically optimizing for two objectives. So obviously you want a solver that minimizes the solving time, but we basically choose these two objectives because we found out that this gives us better results and better diversity in the population. So we basically have, say, runtime per iteration, which basically maps to how cheap or how costly the solver is. And then finally the convergence factor, which, so how fast the solver converges. And So we use this multi-objective optimization, and finally we have finally we get a Pareto front from where we can choose optimal solvers. And so for the optimization components, so so you basically typically you choose from a pool of smoothers. So the way you set up the optimization is you have, say, a bunch of optimal smoothers which you can choose from, and then so a restriction and a prolongation operator, and then a bunch of relaxation weights, and also a choice of coarse-grid solver. And so once you have these different components, you set the population size, maybe so we typically choose 256 or 500 depending on the problem, and then you run it for, say, 100 generations or multiple generations. So some exemplary results. So we basically tested it on a Poisson-like problem with the non-linearity, a 2D problem. So, and we use the full approximation scheme, and we try to see what the optimization gives us. And these are kind of the results. So, the top 5 are the reference solvers. So we basically tuned these reference solvers, and we measured the runtime and the convergence. And the bottom 3 are what the optimization gives us. So we noticed that, so we get more than 2x speed up and faster convergence with these solvers. And this is kind of how the solver looks like for this specific case. So as you can see, so we basically are optimizing for the top 5 levels. So so the bottom, so the 5th level is basically a coarse-grid solver in this case, and we have like 10 levels. So this kind of doesn't resemble any V cycle or a W cycle, and so the white nodes basically represent like no smoothing operations. So basically we do no smoothing steps over here. And so this is basically Gauss, a red-black Gauss-Seidel smoother with a Picard approximation. So because we are dealing with non-linearity, and then so the circle represents a Newton approximation with 1 Newton step. So so as you can see, so kind of having this flexibility in the cycle structure and having the flexibility to choose different smoothers, and also at each smoothing step we also can kind of choose the relaxation factor. So this kind of we observe that this kind of gives us better results in terms of the runtime and the convergence. And the second experiment was basically on algebraic multigrid. So we kind of chose a 3D and isotropic Poisson equation, so which has basically 100 unknowns in each direction. And this was basically evaluated on hyper. So we basically chose like 100 cross 100 cross 100 problem, and did a weak scaling across of 1,000 processes. So the blue line is basically the solver that we optimize, and the orange line is the reference solver that we kind of tuned in hyper. So this is basically a V cycle with optimal smoothing steps and relaxation rates. So as you see on the left, we have the solve time, and on the right, you have the number of iterations. So so as we can see, the solver that we get kind of converges much faster than the reference solver, and also in terms of the runtime, we basically get we are faster than the reference solver. And again, if you want to look at the solver, so again, doesn't conform to any standard multi-grid structure. So just to briefly tell you what the colors are. So we basically have the Jacobi smoother in blue color, the Gauss-Seidel forward in red, and Gauss-Seidel back. So Gauss-Seidel backward in red and Gauss-Seidel forward in yellow. And the white nodes basically represent no smoothing steps. So basically, again, so having the flexibility in the structure and having the flexibility in choosing different smoothing operations at different levels kind of seems to give better results. Yeah, and finally, we also used multigrip as a preconditioner. So this was for the indefinite Helmholtz equation. So here multigrid was used as a preconditioner with by CG star. And yeah, so again, so we also evaluated this over different K values. So yeah, so increasing the K value kind of increases the problem complexity. So as you can see, the lines in the bottom, so basically the blue lines, so these three lines are what we get from the optimization, and the lines on the top is the reference solver. So one thing to note is that we are not only doing better, so we basically, so this the y-axis is the solving time, so we are not only performing faster, but then all the other solvers kind of doesn't converge for larger K values. I mean, it converges, at least doesn't converge for 20,000 iterations or something. So yeah, so we kind of optimize it for a smaller K values, and it kind of generalizes well over larger K values, and where the reference solver kind of fails. And again, so if you look at how the preconditioner, multigrid preconditioner here looks like, so again, it's kind of very sparse, so not a lot of operations in all the steps. So the white nodes basically refer to node smoothing operations, and the blue nodes are the Jacobi smoothers, and the red nodes are the red-black Gauss-Seidel smoothers. So again, we have kind of a structure that is not recursive, and yeah, so not a standard cycle structure with different smoothing operations and different relaxation weights, and this kind of gives us better results. So I think I'm really almost done. So basically that's all I have. Probably was pretty fast. Yeah, so I think the takeaway is that basically having this flexibility in the multigrid solver in terms of the structure and having the possibility to kind of choose different smoothing operation kind of gives us better results. So this is probably something that can be leveraged on maybe existing simulation codes. So that's all I have. Pretty fast.
Yeah, always. We have plenty of time for discussion, actually.
Yes. Okay.
So, do we have any questions on Zoom or in room? Yes.
Very nice talk. With the danger that I'm asking something stupid, and can one somehow understand the choices that the optimization did? So why you have the different smoothers and whatever at the different stages of your cycles, and then maybe learn something from that, and then.
Yeah, I think that is the idea. So I think that's something that we plan to do, but haven't like, yeah.
I mean, if you look at this, I mean, it's just a random collection of colors, but why does it do it that way?
I mean, so I don't have a, I mean, at least, so I don't think we have done much analysis on this part, but I think Uli has.
Yes, Uli, please go on.
He has something to say.
Keep going with the discussion. I have a question going in a different direction, and it should not only be me.
Okay.
But maybe I can add on the answer of Dinesh. So in principle, this is of course what we're trying to find out. Why are these cycle types better than others? But so far we were not really, we do not have a good answer to that. So of course there could be now LFAs or local Fourier analysis done or whatever. We looked at it already, but so far I think it's unclear. So this is ongoing research. Also because the optimization, of course, is black box, right? So you get something and then you have to kind of afterwards, think about, does it make sense or not? Yeah. But this is not yet done.
Okay, Uli, it's time for your question.
Okay, so Dinesh, had you included in the optimization also a standard Gauss-Seidel, which would be sequential, so not good for parallelism, but just to try out in terms of convergence?
Yes. So I mean, at least in the non-linear case, I think that was included. Yes.
And have you tried over relaxation, or did you only try under relaxation parameters?
So over relaxation also, so both.
Say it again, I didn't understand the acoustic.
So I think both over as well as under relaxation. So yeah.
Because I guess in the 3D case that you did with hyper, this is an anisotropic case, and it is known from the theory that a modest over relaxation with Gauss-Seidel should be helpful. And that brings up kind of the follow-up question. I assume that the coarse grid selection in hyper was always the same, right? That was kind of pre-given.
Yes. So I mean the coarse grid solver was basically Gauss elimination that was fixed. I mean, you changed it, but at least in the optimization, the coarse grid solver was kind of fixed.
And
but
not the coarse grid solver, but the coarse grid selection, kind of this, dominant selection of which nodes go to the coarse grid and which not.
Yeah, I think that was pretty much prefixed.
Because I think ideally you would also kind of try to optimize for both coarse grid selection in combination with the smoother, because kind of this over relaxation would relax the difficulty to find good coarse grids. So you might get away with kind of maybe a faster coarsening or something. But this is maybe looking too far into the future, because likely putting the coarse grid selection into the optimization is too complicated to do.
Yeah. So at least
maybe Harald can comment on that. Did we ever speak about something like that?
Yes.
I mean, just to like maybe complete. So at least in this case, so we are only optimizing for the solve phase. So the setup phase is already done. So
okay.
Yeah. So I mean, you're right. So the coarsening strategy is not part of the optimization process. Yeah.
Yeah, but what I can add, yes, next steps would now be to, for example, consider more smoothers, more coarse grid operators, interpolation operators. So just make it more complex. Also look, for example, at the Stokes equation.
Yes.
This question, of course, can you explain it? Is there an analytical reason for it that always comes? I think the real big problem is here in our method, right? So as soon as you start doing genetic programming, it's a heuristic search. So it's not so easy to figure out then. What I would basically, that's my last remark, also would like to see, I discussed it with Dinesh, is a comparison to full multigrid.
Okay. That should be easy to do, and then we should definitely do it. I have one more question remark. How much does the optimal cycle structure depend on the class of problems? So for example, on the class of right-hand sides that you're considering. Because let's put it another way, you might want to optimize for the worst case, kind of the worst right-hand side should still run best possible, or you might optimize for the class of problems at hand, which means you would restrict yourself to right-hand sides that are typical for your problem class, which might lead to quite different strategies.
Yeah, I mean, at least for this case, so the optimization was only run for a single right-hand side. So I mean, so we evaluated on like different right-hand sides, but then at least the optimization was fixed for, say, a zero right-hand side. So but at least from the different experiments, like We also tried using this as a preconditioner, and it seems like the structure is kind of critical in the performance. That's what it seems like.
Just another question. How sensitive is it to the boundary conditions? So if you have solve the same PDE with different set of boundary conditions, with that, is this still an optimal way, or then you need to do the optimization again and see what is the best strategy?
So I think in general, at least, so I mean, so it's not relevant on different boundary conditions, but at least in general, I think it seems to like generalize pretty well over a specific class of problems. So obviously, if you change the PDE completely, probably wouldn't be optimal. But if you kind of change, for example, here the coefficients or the right-hand side, it seems to still work pretty well.
But I'm not talking to the right-hand side. So if you have a boundary value problem that just propagates from the boundary, then you have different sets of boundary conditions. Maybe Dirichlet type on some area and then Neumann type on some other. Would that be still optimal, or it just can be just generalizable into a CFD solver? Because then probably you will have different boundary conditions that you should be able to handle. And if it's just only optimal for one case, then I don't know. This is just a question, is it? Or
so I mean, specifically, I mean, for a specific system, I mean, so I don't have the answer.
So maybe I can comment on that. So what's the whole idea behind it? So of course, if you have any problem, you can just use V-cycle, whatever, so standard cycle. But then if you more often solve similar problems, then it may make sense to optimize your cycle type towards these problems, because obviously multigrid is dependent on the problem. And then you will also get a benefit. And of course, the more you optimize it, maybe the less optimal it is for other problems, especially if they are far away. So I think that's the idea behind it. So you specialize if you have always a certain class of problems.
thank you.
It should, by the way, be typical in a CFD application where you do time stepping, and kind of in every time step it looks kind of similar.
Yeah, exactly. That would be a perfect use case.
Dinesh, in terms of multi-grid preconditioner, have you sought to play a bit with precision? Did you explore it?
Not yet.
Okay. Good. Thank you very much for nice talk and nice discussion. It's lovely.
Thank you.
So now it's my turn before the break. I have slightly different presentation. Okay. Able to see it. Now I need to master my computer to make it full screen. This. Oh, yeah, okay, ready. Seems to be good. Okay, so hi again. My name is Roman Kimchuk. I will be presenting a work that I have been doing and that I'm excited to do is a tool-driven approach toward mixed precision and sustainable solvers for CFD codes. Sustainable means here energy efficiency. So this is a joint work from Pablo Oliveira. Pablo is developing a tool. I'm giving him feedback of what is there, what is missing, and we are doing this loop cycle. And what I would like to start that on the way here, I found this article from Spiegel. So there was PISA test of a report that Germany is thinking in terms of school ranking in math. And that is actually pretty much what I was doing. And I decided to start from this simple example: 2 + 2 × 2 = 8. Yeah, it depends how you schedule, where you put parentheses. And actually, this is a way that I will use this example later on to show that the arithmetic that we are using on computers is lacking this property that is called associativity. And that's what I will be building on top. And to start even more in interesting way, I would like to touch this topic of numbers and counting. My kids are counting 1, 2, 3, many. And we humans, scientists, using 10-base system, and this is quite old system. originating with from Persia, Arabic, and that's the reason for that we have 10 fingers, and that's one sort of motivation or strong motivation for that. Some countries have access to toes because they live in better climates, like Mayas, France as well. And to my surprise, it was like that Denmark is using 12-base system in order to express some of their numbers. But computers that we are dealing with are using binary system, and that actually brings us to some complications how computers are thinking. So we see the mismatch on this slide from 10-base system to binary. I will elaborate about it in a couple of slides, introducing you to floating point arithmetic, and then I dive deeper into the analysis of codes and how precision can be tuned. So overview of my talk is the following. We'll start with floating point arithmetic, then I will provide you with some definition of sustainability, and I will define an approach toward it. I will show the steps that we are taking, and I will provide some preliminary examples how precision can be analyzed and what are the possibilities for precision tuning. So binary numbers. Yes, this is a courtesy from a slide from my colleagues that we were teaching scientific computing, and we have this introduction course. And what is important here is to see how actually computers are treating numbers. So computers have two modes, on or off. Yeah, pretty much this is what is motivation for binary numbers, and we have ones and zeros, and that's over here. What we have is a base. So we represent these 4 bits. Then we can actually unfold them and convert them to the decimal representation. And going from binary to decimal is always exact, but going from decimal to binary is not always exact. And this is where the problem actually starts to occur. So what we take, we take 1 times 2 to the power of 3, because here the highest number. Then plus 1 times 2 to the power 2, and so on, and then we unfold the number and we compute 3. The same can be done with fractional binary, as shown below. Pretty much the same way, we put comma or dot here, and then we get our decimal number. However, there is a warning that some numbers cannot be exactly represented in binary format, and those ones that are often used as stepping in methods, in iterative methods, or different schemes like 0.1, and so on. But 0.5 is like 1 divided by 2 is fine. And this is like an example. So we can just do slightly small modification in order to not lose accuracy where it should not be lost. So that's the idea of this slide. So we can, instead of using stepping 0.1, we can start from stepping 0.125, which can be exactly represented in binary format. So that's the first part of the message, and the second part is that we are dealing with computer arithmetic, and we always have to feed this finite format. So we have to truncate, and truncation calls round-off error. So we are losing some information, and here it propagates to the loss of mathematical properties that is called associativity. Commutativity A times X equals X times A is still fine, but associativity that is defined like this is not preserved, and this is due to the fact that we cannot store all the information. Here's an example in double precision. So we are adding 2 numbers, -1 + 1, so we will have cancellation over here, and on the left-hand side we will get 2 to the power -53, while on the right-hand side we will get absorption, because when we add 1 + 2 to the power -53, does not seem to be large numbers, but the format doesn't allow us to store this last bit that is represented 2 to the power -53, so we're over here, and we have to truncate it, and that's why this result is not equal from both sides. And so on the right-hand side we will get 0. And it actually propagates in such a way that summation, for instance, if it's done in ascending or descending order, it depends, the result can be different. So if you're talking about positive numbers, then ascending order would be the best one. So we start with the smallest one and we carry our error towards the largest one, while when we have different numbers in magnitude, we may have cancellation, and then descending order would be better. These ideas are not obvious, but when you play, when you touch numbers, you see it. And the consequence and message here is that, especially when we project toward parallel computing, that the result and accuracy of computation depends on the order of computation. It depends how we divide, how we parallelize, and so on. However, there is some, this is floating point arithmetic, some limitations that we should probably be aware of. But there are also some nice works that how to overcome it, and then I will be sort of tilting right now towards that. But before doing this, I would like to introduce you to some 4 formats that people often operate when they do scientific computing or related to it. 3 top ones are defined in IEEE standard for floating point arithmetic that was finally revised, had second revision in 2019, and included basically binary 16. So operating with 16 bits. We know double precision, 64 bits. We have 1 bit for sine, 11 bits for mantissa, and 53 bits for fraction or exponent 11 bits and 53 bits for fraction or mantissa. The first bit is hidden, so that's why physically we have only 42 bits. We have single precision, and then we have only 23 bits for precision. So fraction represents precision of our computations, and then exponent represents a range of numbers. What is the range of numbers that we can cover? These 2 formats were motivated by sort of advent of AIs that started using heavily computing resources, and this format was sort of born due to the demand. And the first one is actually the precision. The idea here is the precision was not so easy. However, it turns out that what those AI applications required is to have a range of numbers, but not precision. And this format, half precision, was not sufficient for them. And just if you think about half precision in arithmetic computations, that you can think about 10 to the power minus 4, that would be the best attainable accuracy when using this format. While with single precision, 10 to the power minus 8 and double precision minus 17. That's why was some sort of combination of half and single was brought, and it's bfloat. It's not adapted to standard, but it offers nice possibility to have a range of numbers as in single precision, but fraction is much smaller because we're just looking for direction. Good motivation, and in terms of application to scientific computing is still a debatable question. So with this information in mind, I would like to introduce you to mixed precision. I will provide you through some sort of history what is actually happening and how precisions were mixed through this line. So you can imagine here the lines that represents how many bits we can allocate to our format or to our computations. The lowest possible amount would be 1 bit, but we are not touching that, just indication. And initially we had sort of double single and plus iterative refinement. So double, we were computing in single, and double was used in order to refine precision. And that is quite known approach still from works in 70s. That has been extended recently with the new precisions coming out, and there are double, single, and half precision, even using bfloat. And there is very nice overview of this precision. So that is pointing towards what is actually happening on the horizon. So it's like overview, and looking on this article, we can see where it's possible to take a look. And there are works that are spanning both experimental, just trying and see whether it converge toward thorough and rigorous numerical analysis using up to 7 precision, which is, in my opinion, is not realistic. We can play only with what we have in hardware in order to really get benefits of performance that is provided. So that's the current picture, but we were not always in such a situation. So we know about some sort of sometimes we have a need of higher precision, and then it also can be extended in the other direction in order to increase precision. And the common way would be to use quadruple precision or FP128. It used to be that some hardware vendors adapted it, but now it's only emulated by software. We can still even emulate it by using an array of doubles, 2 doubles, and then we can play with them using error-free transformation. So we basically keep track of error in order to not lose information. And the other possibility was to compute, as we are dealing with large register, with a large vector, and it's called long accumulators, that was has its roots to here in German, Karlsruhe Institute of Technology, and the scientist that is named Foolish. So with this and with this spectrum that I provided to you, I would like now to define what is mixed precision algorithm. So this is an algorithm that carefully, effectively, and safely combines multiple precision for the sake of optimal precision usage and convergence of algorithms. And here we can play with two factors. Numerical analysis would say accuracy first and stability first, but those people who implement on hardware can say performance first, and then accuracy can be sort of traded for performance. So that's what is the current state. In terms of sustainability, something that I got excited, and this slide probably needs to be updated, about high performance computing. If you look on the history and development, it was actually quite nicely shaping and moving towards energy efficient architectures. So we have GPUs, FPGAs, etc. And we also have some nice methodology and techniques that help us to sort of reutilize, to be sustainable with respect of footprint of energy power consumption of centers. So for instance, at PTH, extracted heat can be used to warm up as a campus, or free water can be used from a lake or any sources in order to cool down supercomputers. In northern Sweden, we are lucky enough to have colder weather. Just a joke aside, open V2 to cool down supercomputer, but there are different opportunities to think about, like, the whole ecosystem, as HPC as a whole ecosystem. And algorithms play important roles there as well, because exascale computing is constrained by power consumption. We have different architectures that are moving or looking towards it. We have ARM-based CPUs that have already natively 3 different precisions. We have a European processor initiative with different technologies that are supposed to be energy efficient technologies. But on the level of algorithms where I am working and where I'm playing, what I noticed that linear algebra was predominantly viewed and measured in double precision. And then now it's time for sort of revisions that is going and undertaken. And this revision is like 3 stages, not on algorithmic level, so mixed and adaptive precision computations, on level of implementation, communication, hiding and avoiding. This is what we have heard from the first talk from Niklas, that he implemented this communication hiding method, pipeline method, as well as tools. We are used to use tools for monitoring memory consumption, memory leaks, etc. And there are also, I would like to pre-open a window of opportunities for you to use tools for inspection of precisions, and then based on this information, try to change algorithmic solutions. And my approach that I'm advocating is to, instead of blindly playing with variables, sometimes it's needed also to inspect, to run a tool, and there are plenty of tools that I have access. I'm lucky to have access to Interflow project, French Interflow project, and I can inspect the code with the tools. Then the tool gives me an output, and on this output I can see, okay, what is a reduction in precision is possible. If it's possible, I can combine different precision on granularity of function. Also, it's possible to zoom into variables, and then I can derive algorithms. So this is the first 2 points. The third point is actually something that is emerging right now, is called probabilistic error analysis and stochastic rounding that is supported in hardware. Stochastic rounding is cheaper than rounding to nearest with breaking types to evens that we are used to use commonly. So it's like rounding to nearest, but stochastic rounding is like flipping a coin. We cannot predict which way it will go. But according to Bernoulli distribution, we can see that with probability 95%, we will get certain estimates. So we can cover most of the practical cases. And then what we, in terms of error analysis, we can put square root of n of the problem at hand, not of n as we have usually for rigorous analysis that is based on rounding to near. So there is a gain from numerical analysis, there is a gain from implementation, faster implementation, but there is also a gain to avoid this accumulation of errors that is happening with rounding to nearest. So my focus would be here on the first 2 points, analysis of the code, and try to see whether there is a window of opportunity to have precision reduction. And let me quickly guide you through a few slides about it. The tool is called that I'm using is called Verificarlo, and it's an automatic tool for debugging and assessing floating point precision. It has 2 backends. One is based on Monte Carlo arithmetic, it's called MCA, that puts noise into input data, and then we can see how sensitive our computations are and whether they can converge. The other one is VPREC can produce already mixed precision binary, so we can run it, and then we can see what is actually occurring. And with help of this tool, we can actually put a request how much bits in mantissa or exponent we require, and this will be residing in larger data type, and then we can conduct our simulations. And here an example, and motivating example how it works. It's a Newton-Raphson method or similar, quite good examples for this. So this code on the right shows computations of inverse of pi. And when we start with our initial approximation over here, we have k iterations, we have approximation 0, and then here we have engraved some bits that are sort of not useful because we have no information about them, but we still fill our double precision format. Over the course of computations, we, from iteration 3, actually we start doubling the number of correct digits, and then here we compute how many number of correct digits we have in decimal or binary formats. And if you look on the simulation overall, so this is pretty much the required accuracies that we are having, require useful accuracies that we are getting, and over course of computations, and with the help of VPREC, and in terms of convergence history and speed, we are actually matching the initial code. So that's sort of a motivation for me. But in terms of real problems, I would like to, or semi-real problems, I'm zooming into Neckbone solver for Poisson's equation with conjugate gradient method using different preconditioners, and I'm also examining flexi code with high order accurate code, open solver for PDEs, hyperbolic, parabolic types. It's just preliminary studies, and I would like to guide you through it. So this is a basic example. Solver is CG, and unpreconditional. See here schematic solver that we have on the left-hand side, and I was observing this variable, scalable variables like tau and beta, etc. And I was plotting, creating a plot here on the bottom. X we are plotting precision, on an axis Y we are plotting the value of variable, and here since it's spectral method, we have different number of elements. So higher is better, and here we have plateau. So it means when we vary our number of bits for mantissa for precision, we can see that starting from 10 bits, we are sort of getting stabilized results. So it means that the precision starting from 10 bits is sufficient, or actually 11 is sufficient to carry out computations. I went for a bit more complex example that I found there. It's a multi-grid preconditioner, and I did the same simulation. So the method solver remains the same, but we have more elements and a bit more complex situation. So here the situation stabilizes from 14 bits. So it's actually indication that here we can safely sort of drop precision and set up like single precision example and try to switch from double to single precision. Of course, this is a toy example, but that is actually gives me some intuition and opens a playground for larger codes. And what I did, I set up precision to single precision, and then I conducted simulation with another backend in order to perturb this simulation to see how the variation, to introduce some noise in simulation and engage Monte Carlo arithmetic, engage 20 samples, and to see how it actually behaves And here we can see two lines, one black line and the other one is a red line. Black line is double precision, red line is single precision, and there is an error, sort of bars, but they are too small, so it actually the single precision was sufficient enough, and the noise that was introduced by verificarlo didn't perturb the simulations. The other example was much more challenging and took quite a bit of time to set up, and it's fun. So we are solving the Navier-Stokes equations, and we are using ODE. So we are using explicit Runge-Kutta method. And here, we are simulating Taylor-Green vortex TGV. And what happens here is actually the simulation. We were mimicking simulation in order to have runs within 5 minutes or so. I was observing important functions that are doing computations over there. So the problem is explicit methods that when we got error, we carry through the whole simulation. So it's actually quite sensitive. And but no one has done it so I decided to start with this one, with challenging one. And I was playing with precision tuning or accuracy precision from 53 bits towards 20 bits, but I started getting an error that implementation was detecting that something is going a bit shady, and then I got this error that the basis of were not computing properly, and then the simulation stopped. So then in order to intercept the whole solver, I focused only on some few functions from discontinuous Galerkin method, and then those functions were computing surface volume and source contributions. I zoomed there, and we found for small case we have domain split on 4 parts that is not quite working well. So perturbation in precision, if for instance I reduce to 23 bits single precision, we have we are not covering properly the edges of this domain. So when it connects, and this is where the error actually propagates. So here we have different domains. We zoom on them and we track one point, and we just track velocity over there. Here's the value of velocity, and we can see I plotted an error in red. With the help of my colleagues from Stuttgart, and we zoom error by 10 times, but the error is too big in order to reduce this. So this is actually still ongoing work, but with explicit solvers it's much more challenging. So it's very likely that on these functions we would need to zoom in and try to play per variable, because and try to see what actually occurring there, how to play with the precision. So with this, I would like to put a brief summary. So like what I learned from it. So mixed precision is definitely the way forward to energy efficient and sustainable computations. Tools are helpful and can provide estimates and ideas where we can tune precision, but they are working per case base. So one case, one solution, and then we need to think about numerical approaches in order to have adaptivity for different cases. So mixed precision adaptive solution is the way forward. And the other part is computer tools are useful, can be employed for different ways to detect abnormalities, precision inspection, but also numerical CI. So that's the message from my talk. Do you have any questions from Zoom or from audience, or any comments? Actually, would be also good to hear.
What is CI?
A continuous integration. So if you run your code, if you make some changes, you commit, and then you try to verify that not only performance is preserved, but also numerics is not damaged. Yeah. Yeah. Yes, precisely. If not, then I would like to invite those who are with Zoom on Zoom with us. We together with Sally, we wrote a very nice article about mixed precision. So we try to write it like in a bit popular science. So please check this article out. And there is very nice information, for instance, how you can count with in binary, like in basis like computers using your fingers. So it's fun to read article and to play around. Otherwise, if there is no questions, I would like to have a break for about 15 minutes. I propose to have a break for about 15 minutes, and then we meet at 1535, and we will continue with the second part of talks.
The article for helping you explain what you do to people who are not experts.
Yes, yes, certainly.
All, I'm sorry. First of all, what you have to do, you have to change the interface. How your gather scatter, this direct stiffness summation works. Previously, we had just QQT operators that allowed us to go from local to global and global to local representation, exchanging information. Now we have to include additional interpolation operators, JL, as well as it's transposed. However, our tests and our experience with NEC 5000 showed that for the pressure calculation, we had to as well include the inverse of the interpolation operator. And that's how those operators are defined. For the brevity of time, we will not go into the details of that. That can be found in the number of papers and works related to interpolation and spectral methods. The other important stuff which we have to change, we have to work once again on the mass matrix. As I mentioned, the mass matrix has to be a diagonal one because during the pressure iteration you need to invert that. However, the non-conforming phases change this feature of the mass matrix. It doesn't change the internal part of the block structure of the mass matrix, but due to the non-conforming interfaces, the global mass matrix is no longer diagonal. So we have to perform an additional steps for the lumping of the mass matrix that would allow us to have the quick inversion of it during the pressure solve. And the last step is when we talk once again about the pressure solution and about the coarse grid solve. That was once again mentioned by Niklas when he was talking about these two levels. For the coarse grid solve, we actually have to build the global matrix. And for that, we have to perform a mapping from the data inside the element just to the vertices. And for the conforming phases, this operation is extremely simple. And actually, you can see number of the conforming, how it would work for the conforming interfaces. Those are those round functions, because what you have to do, you have to simply do the mapping of your big number of degrees of freedom on some base function, low resolution base function, and simply convert your data into the single vertex information. For the non-conforming case, this kind of operation is no longer local operations because the shape of the function will start to depend on the topology, into what way the refinement have changed the mesh. So this is the last important part that has to be changed inside the non-conforming solver. So when it comes to implementation, we worked for a number of years with NEC 5000, which is well known and actually mentioned today as well by Niklas, spectral element solver. It has a long history of development, and as well it scales very well. It's, however, a little bit old code in the sense of the coding. It's mostly Fortran 77. And that was our work for a number of years. So what we needed to add, in what way we had to change the solver, first of all, we had to add an error estimator because you have to know where to increase the resolution or decrease the resolution. Then you had to add the grid generation, some kind of grid manager that would allow to read the information about the grid quality and then change the mesh, grid partitioning, because the new structure of the grid cannot represent properly the mesh distribution. So the work balance would require to repartitioning of the mesh. And then, of course, you have to regenerate your mesh. You have to start to transfer and sort your data. And at the end, you have to restart your solver. So for error estimator, we used spectral or adjoint. I will only say a few words about the spectral error indicator. Then for grid generator, for NEC 5000, we used an external library, which is called pForest, and this is the library that allows you to provide an oct-tree refinement. And for grid partitioning, we use Parmetis or the native 5000 partitioner RSB. So when it comes to errors indicator, what we looked for is so-called spectral error estimator, which was developed by Kathy Mavropoulos a number of years ago. What it simply looks is the coefficient of the Legendre distributions, and it simply tried to look into the tail. So it simply tried to expand the expansion coefficients of your base representation in your base functions, looking into the tail. What would be the assumed shape of the decay of the expansion coefficients, and then it simply tries to estimate this missing part of energy inside your flow. And if this missing part of energy is too big, it simply marks the element as the element for refinement. And then when you have the refinement flagged elements, you have to, of course, give it to the library. And pForest is simply a pretty well developing and pretty well written library for oct-tree refinement, and simply take a mesh and allows you to divide every single element in the recursive way, in 2D into 4 elements, in 3D into 8 elements. And it allows you to build a tree structure. You start from the coarse grid, and then every single element can be refined, and after that, refined again. So when it comes to our implementation for NEC 5000, it was pretty effective. For a number of runs, which were not maybe extremely big, but relatively reasonably big, we found that the time spent inside the AMR refinement was less than 0.5%. Of course, this will depend strongly in what way would you do the refinement. In this case, we are not interested in following the feature, in tracking the structures inside the flow, but into finding the static mesh at the end of the simulation. But the cost of the non-conforming solver and the whole simulation was relatively small. And here I will show like 2 different examples of the runs which were done. This one both of the examples are actually the examples of the one of the Exerat phase 1 project. This was extended and run by Siavash Tusi, and that's his result. When you have the wingtip with the rounded tip, and you see the mesh structure on the side as well, you can see very nicely how well resolved this flow is when you have all these wing tips, vortices as well with the secondary and third vortex. The other kind of simulation, which was once again run during the Exerat phase 2, was the simplified rotor with 4 blades, which is to some extent similar to the previous simulations because the airflow, the blade structure is similar. And on the left, you see the different refinement levels, how they were embedded inside that. And they show that in what way the refinement is localized. And on the left, you see the nice lambda 2 representation of the structures. So of course, now we go to the current work. I will not describe NECO because that was well done by Niklas already. Of course, what is maybe important to mention here that the jump from NEC 5000, which was written in Fortran 77 with a way simpler structures, to NECO, which is a modern code with a way more complex structures, it's not a straightforward one. So what we have to do with NECO within actually much shorter time is more or less the same we had to do for NEC 5000. That means we have to use the error estimator, and this we can use like the same way like for NEC 5000. Then of course we need the mesh regeneration, and that is done once again with pforest and grid partitioning for Parmetis. So what we have to do mostly now is to couple NECO with all those parts and to rewrite NECO into the non-conforming solver. And of course, the first important part is the mesh regeneration. And what you see here is the current conforming mesh class diagram for the mesh description inside NECO. And it mostly is related on the point description. And there is a little bit of the problem when it comes to combining this with pforest because it's not non-conforming mesh specific. So one of the work we are doing right now is rewriting this mesh representation inside NECO so it would feed nicely into the pforest and non-conforming structure. There is a little bit of work of that, and this work is under construction right now. Unfortunately, the complexity of the class and of the type increases in that case. So what is the general workflow we are going to work with? First of all, we have to collect our error indicator. This has to be done on GPU. Then we would perform the regeneration of the mesh with pforest, but this would be on the CPU. And then we have to reconstruct the simulation variables on GPU and restart the solver. And the main challenges which we would face here is actually a problem with the interpolation operator. The problem comes from the fact that the non-conforming interfaces, which are used during the direct stiffness summation, you have a relatively small amount of those interfaces, and those interfaces are in more or less random way distributed among different elements. So in that case, the interpolation operation, which acts on the small amount of data, is really challenging, and this data is scattered along the big arrays and difficult to do. So what we have to do is actually we have to find a most optimal way to perform those interpolation operators inside gather scatter, and those of course are the memory latency dominated problems. There are a few ideas how to do this, but that will be kind of, for the brevity of this talk, I will have to stop here. Thank you.
Thank you, Adam. Do we have any questions on Zoom or in room? Yeah, we in fact have not so much, probably one question.
I say I don't see any.
We have Uli. Uli, please go ahead.
Others should have priority, but if I'm the only one, what is your experience? How far does Parmetis and especially also pforest carry in terms of number of elements that you can handle? And is that enough?
Let's say for our experience, for those runs which we've done with NEC 5000, because for NECO the work is only, let's say, inside, we started to work with that. For NEC 5000, we were going into like 3-4 million elements, starting with the mesh of the size of 50,000 elements. So from 50,000 to like the range of 5 million, so quite a lot. And in this case, actually, P-forest was not a biggest bottleneck. The biggest bottleneck was restart of the XXT solver inside NEC 5000. The problem which I can see with P-forest is that P-forest is the library which actually copies the coarse grids, the coarse mesh on each of the MPI rounds. So the initial mesh has to be rather coarse in the sense that it cannot have a big number of elements, because if the initial mesh has a lot of elements, then the performance of P-forest drops. So that's something what you have to keep in mind. But in most of the cases which we were running, the initial mesh was relatively small, in the range of, let's say, few thousand to dozen thousand elements. And then when you expanded this to the few million elements, everything worked fine. With Parmetis, the biggest problem was that sometimes it gave the partitioning that was discontinuous. And then, of course, this influenced the performance of the solver. So that was as well a problem. And some people use two-level partitioners, some more specific. AVBP uses this three-part, which is more advanced, more elaborated on that. But yeah, that's my experience.
Yeah, okay. For NECO, what do you think, what mesh, how many mesh elements do you expect to need to saturate a full exascale machine?
Oh, yeah, that's maybe better.
200 million.
Yeah.
How many? I didn't understand.
200 million.
200 million.
Yes, maybe saying that we did 100 on Lumi, and Lumi is half, so 200 million.
Okay.
Plus minus a couple of millions.
Yeah, but 100 million should be within the range of P-forest. That should be okay. With Parmetis, I'm not sure. Have you used?
NECO supports the 64-bit Parmetis if needed.
Yeah, I know. We did the same for NEC 5000. You reach this level even with a few million of elements when you cannot run Parmetis and longer.
Yeah, this is why I'm asking. So in our multi-grid solver, we are working with lower order elements, and then so to saturate an exascale machine, we expect to have to go to something like 10 to the 12 elements, and then all these methods, of course, break.
No, of course. P-forest supports up to 10 to 11.
Yeah.
Yeah, but we are talking about a few, let's say, orders of magnitude less.
Okay. So thanks very much.
I have to interrupt because we need to follow the schedule. Thank you very much for lovely discussion. And I would like to invite our last speaker, Eddie Wadrow. And Eddie would be talking about topology optimization and spectral methods.
Just I make sure my scene controls before I start. Yeah. So thanks, Roman. I will talk about topology optimization in spectral element codes, or at least this was the original title we submitted. But then after a while, I realized that we already have had two talks about NECO already and the development in there. So my plan now is to sort of say, well, talk a few words about moving towards ultra-large scale topology optimization for fluids. And before that, I would, since not all of you are researching topology optimizations, I will give you a brief introduction to what type of problems has been used for earlier, and what has our first few steps been in pushing these technologies over to work with fluids. So we will here use a typical approach called a material distribution or density-based optimization. And the task here is to find optimal placement of material inside a given design region, here called omega D. So The problem I will talk about in the beginning is to design a cantilever beam, so it's clamped here on the left hand side, and it has a force on the middle of the right pulling it down. And what we want to do is to minimize something called the compliance, which is sort of the inverse of stiffness. We want to make this one as stiff as possible. And to do this from a, say, computational point of view, we take our design domain. Now this is in 2D, so we split it into a bunch of pixels. And then for each pixel, we want to decide, should this pixel hold material or not? And for this problem to be interesting, we will have a limit on, say, the amount of available material. So, and yeah, the minimize compliance, want for each pixel to be 0, 1, limit on the available material, and we have a governing partial differential equation, which here are the equations of linear elasticity. And from a computational point of view, is sort of starting with this sort of binary constraint. It's sort of rather nasty. We don't like this. So I will walk you through the typical steps of doing this. So step one is to relax this constraint and let this design variable attain values in a continuum. And this is sort of, from a mathematical sense, this is very nice because we can now prove that this relaxed problem goes convex. Very nice. Unfortunately, this solution is not just 0 and 1, so we have this black value. So yeah, we get the nice looking design, but it's not manufacturable and it's not purely void material. So the next typical step is to add some sort of penalty. The good news is by adding penalties, we can get a purely void solid design. But the bad news is that from a math perspective, the problem is ill-posed. So we can show that it lacks solution within the set of feasible designs, and sort of in the limit of, from a computational point of view, in the limit of mesh refinements. From a refined mesh, we get finer and finer structures, and yeah, not so good. So next typical step is to add some sort of filtering to impose, the idea here is to impose a minimal size control. So instead of just having the design variable entering the PDE and volume constraints, we take a filtered version of this. So starting off from just, instead of using the design variable at one point, taking a small local average around the neighborhood. From, yeah, this can be proven that if this filtering is a standard convolution operator, we have a solution to this problem. And one can also do it more modern and replace this filter by a nonlinear filter and still get nice solutions, retain that, well, the good sort of, yeah, all the good news today, we have solutions and we can actually get the sharp solid fluid interface. So this is sort of a quick introduction to topology optimization and what we want to do. Well, we need, of course, we need to extrapolate what we want to do for fluids. So a few major milestones by us. So in 2009, we did this on a GPU. So this is for a heat conduction problem. So we're essentially optimizing over a coefficient field in a Poisson equation. So still nice and easy problem. Later on, our Danish friends stepped up and did compliance minimization in 3D for just essentially looking at the interior structure of a wing of, I think this is the Airbus 380 wing, trying to, well, minimize weight, given some structural constraints. And then they have later on moved on to looking at the girder section of super long suspension bridges. So this is sort of for problems in linear elasticity, which is sort of, well, a more complicated Poisson style problem. This topology optimization is, well, it works well, and it sort of has reached the state where it's used in industry and we can solve super large problems. But now we want to move this technology over to, well, in my opinion, a bit more interesting physics. I think we all agree here. This is what we do in mechanics. So my next idea here is to talk a little bit of our preliminary work done in NAC 5000. So it's joint work with Martin and Philip that are already here, and Dan Henningsen at KTH. And the person up here, Harrison Nobis, is the main worker. He will defend his thesis on Friday. And then hopefully we will be able to recruit him into CEEC, but yeah.
That's our plan.
That's our plan. So,
He has no say.
well,
Yeah.
so the preliminary work here considers laminar turbulent transition. So essentially what makes this difficult, it's unsteady, nonlinear, chaotic and turbulent, it's computationally expensive. So lots of stuff makes it difficult, but also makes it fun, right? So then the task here is to delay transition, and there are, well, various reasons to do this. Transport fluid more efficiently, to reduce drag, or influence stall characteristics for vehicle engineering. So it has some applications. What in particular we will look at is trying to optimize so-called super hydrophobic surfaces. And the idea here is that instead of having a, say, a solid surface, is to, on the microscopic level, not have a solid, but have a few gas pockets built in. And over the gas pockets, the no slip condition is no longer valid. So the fluid can sort of accelerate over the gas pockets, which will lead it to, on the macro scale, to have a sort of some slip velocity. So that we will have some velocity there, which will sort of help reducing drag. And so we can actually model this by sort of a slip indicator function. So here the rho that I keep on using the same notation as for the solid mechanics case. So if rho is 1, we have a more slippery material, and when rho is 0, we have a less slippery material. So we can sort of, in a sense, do it as we have two paints, well, with one has finer and one has denser structures. So let's say, and the questions we aim to answer, well, if we have these paints, can we paint a pattern that delays transition further than homogeneous counterpart? And can we find this pattern with topologization? So, spoiler, answer is yes to both. But how to do this? So we do a case setup. We have a 3D computational domain. We do the Navier-Stokes equations, looking in a span-wise periodic case, consider subcritical channel flow. And the 2D optimization domain is the top and the bottom of this channel, on which we want to figure out, if you will, how to paint this in order to delay transition as much as possible. The inflow, we sort of use an analytic base flow based on the current slip length. So essentially what you can see here is just, if you increase the slip length, the base flow changes slightly, but and then to trigger some sort of transition to turbulence, we do not just use the nice flow, but we add 2 small instabilities. So these are sort of induced at the inlet. So we have the primary and the secondary instability, where the primary instability we induce this by a large number and the secondary by a smaller one. And then we see sort of how these grows with time or space. So they're sort of just drawing some the Reynolds tau number, which essentially tells us, well, how this, you can see how this grows and where sort of the turbulence is being triggered. So we have sort of by random selected at 5.5. This is where we consider the point, where it goes over to turbulent, and this is when the Reynolds tau number is over 150. So looking at the sort of powers of these modes, so we have the primary instability that we induce, it doesn't grow, it sort of stays flat, whereas the secondary instability that was induced is a very small thing. It sort of grows, and then at some point we see that this goes big enough, and we get turbulence in the plots. So the red and the blue are essentially just trying to depict how the fluid moves at close to the bottom and the upper part of this channel flow. So to delay transition, of course, in the turbulence region, everything is chaotic. So what we do is that we look at the beginning of our domain and look sort of over one period and try to, as a proxy for, let's say, delaying turbulence, we minimize the pseudo dissipation function over this sort of over one, of this block essentially. And here comes sort of the optimization algorithm. This is what has been done in NEC, and there are many of these things that, well, I'd say from a software engineering perspective, it's not that nice. It's more like duct taping it on the outside of NEC, like 5000, hoping that it would work. And now, sort of entering much earlier in the states of NECO, I think we have chances to do something really good here. So essentially, we start with an initial rho. And in this case, rho, so one major difference here between this and the structural mechanics case is that we will not use this as a piecewise constant in each element. but actually use this also on the spectral element grid. So the rho will actually be interpolated by a higher order polynomial, and then we filter this one to get the size control. Also, and this can be either done by a convolution filter or by solving a strongly elliptic PDE. Both of these will also go into the NECO code, the steady forward code, and then an unsteady forward, an unsteady adjoint to get the gradients, steady adjoints, combining the two solutions from this to get the sensitivities, and update rho using an optimization method called method of moving asymptotes. So there are quite a few things that needs to be pushed in. Well, parallel versions of this will need to be pushed into NECO to get this to work, but this is the plan to do in the next few years, and there will be people working on it. So I just want to show you some results from the convergence history. So I have a picture of the bottom and the top layout, and the dashed portion is the optimization domain. And remember that this is here is a periodic structure in the Islamic direction. So as we go forward, we can see these sort of parts growing, and there are a few interesting things to note. So on the optimized design, so it's not top-bottom symmetric. It is larger than, say, the length scale of this primary instability. The sort of the good news here is that it actually does transition 29% further downstream as compared to the one using the more slippery hyperhydrophobic paint all over as a homogeneous ping. And it inhibits the growth of the secondary instability modes. So all these are good news. And if one looks carefully at how the flow actually looks for these cases, so I have no slip, little slip length, big slip length, and the optimized one. So in all of these three at the top, we see these sort of K-type symmetries where we have this sort of lambdas forming here, or V's forming in all three of these. And the optimized one, we have sort of V's forming on one side and lambdas forming at the top and the bottom respectively. So this symmetry is being broken. So this is sort of, if we were to guess, this is sort of what we guess that the optimizer is doing, and by breaking symmetry, thereby delaying transition. And yeah, so so what are we currently doing in this project? So there is thus far one PhD student, postdoc recruited. It's Tim Philip Olsen, who is now getting acquainted with NECO. So he has been kind enough to provide him with this picture, which is sort of like a mixer-like geometry, because in the end we want to do Lighthouse case 3 and optimize a mixer, which now is just modeled by a solid block in NECO. So it's a convection-dominated scalar transport for a mixer-like geometry. We're starting to look good. The plan for the next year is to recruit 2 more postdocs to work on this and really get started. So far, we've been mostly working with finalizing the old stuff in NAG 5000 and also looking into stable adjoint solvers, planning what to do next. And yeah, as I promised Roman, I should not talk too long, so I talk fast.
Oh, it's actually good because we have time for discussion, and I had to interrupt another discussion so we can come back to that. So thank you very much, Eddie. It's very exciting. It's a general way.
This time, glad we didn't get a wolf.
Well, do we have any questions from Zoom participants? So the mixer is quite different from this cube. How we are going to represent that as a topology of a mixer? It's quite complex topology. How?
Yes. So as I said, so we will take this sort of the design function, the role will now be described as with in the same basis as the flow fields in NECO. So it will be on each spectral element we will have a tensor product function for this, and we will of course optimize over all values there. And of course the nice thing with the piecewise constant is that if you look at the design variables and you have a minimum of 0 and a maximum of 1, you know that it's just constant, it will never be above or below. But for spectral elements, if you just look at the nodes, you could actually have over and undershoots. So that would be one challenge to get this into, say, the immersed boundary or the fictitious domain code and seeing, well, how to get this penalty in. So far, we've been using a Brinkman term for this, but we will also look into other ways of getting better immersed boundary matches. I think Philip, your lead on that one.
So I told our internal meeting said that we will.
That we will do this together, of course.
Focus on the Brinkman term, but I'm happy to do.
Yeah.
We will start with the Brinkman term.
We will start with the Brinkman
That's
term.
what we know how to do.
Yeah,
And then we will see.
and think of many other things, because I think also like with all of these projects, there are so many interesting challenges, and we need to, I'd say, well, deliver a bit, but at least deliver what we promised in the end, and maybe not do all of the cool science directly, but
No,
the one that we need to deliver results we will do.
that sounds exciting. Yeah, nice. Any other questions to Eddie? Uri and Adam, sorry, I interrupted your discussion. Now we have some time for this, if you would like to resume. If not, then I will provide some wrap up and some sort of concluding remarks, and what I would like to share with you is actually how to seek us out. I like this expression. It's really, yeah, exactly. It's really super cool. While you will be looking on this slide and typing these links all the way along, I would like to provide some brief summary what we shared with you today. So Nicholas presented advances in NACO, how asynchronous communication and how overlap of communication computations can give you better scalability, and also how you can use computing resources wisely when you can even overlap computation stages. So that's quite cool, especially for this pressure preconditioner. Then we had a second presentation from Dinesh. He was talking to us about grammar-guided way of optimizing computation flow in multi-grid solvers. If that was quite exciting, and especially it can be quite handy when you think about iterations that are conducting computations over and over, performing the same computations, and that's quite nice, especially when what would be really interesting from my perspective to take a look on when a multi-grid is used as preconditioner, and whether we can dump proc precision a bit there and use it with the BCG step, so to see how it is working. That would be I would like to discuss this and to see how it actually converges. From my side, I was talking about computer arithmetic, giving you some another look on it, and I wanted to open sort of a window of possibilities. Instead of empirically playing with precisions in codes, we can use tools in order to have a better overview of what can be done, and the tool can actually be zoomed and can be used only per function level, so that this actually gives very nice granularity and can provide statistics. With small applications, it's quite obvious. With explicit solvers, it's not so obvious. We are still working on that. There is not much literature on this, and what we will be looking forward right now is on inspection. We are doing it on the ways on inspection of NACO and implicit solvers, where we have iterative solvers that can give us better benefits. Then in the second section, we had presentations covering fault resilience, how tools like Liquid can provide us with some measurements that can be useful, and that temperature of course was quite nice, and this is what I remember from it. And the second presentation, and we are looking now how to extend this idea and concept towards GPUs. The post presentation was from Adam. Exciting. I finally understand much better what the spectral methods are, and then why mesh edge adaptive mesh refinement is necessary there, and what kind of effort and lift is you are doing, and that's quite impressive. And this is about coupling a mesh manager with Neko and try to do large simulation with that. And the last talk was about topology optimization, how it looks, what can be done, and looking towards mixer, static mixer. So it's everything is excited. You can sign up actually for newsletters. That is the second bullet, and we will not be spamming you, but I think Sally, we will be sending once per month, or maybe even.
It might even be less, it might be quarterly, but yeah.
Yeah.
We'll see. If we have more to tell you, we'll probably be a little more often, but at least for now, probably quarterly.
Yeah, great. And then we have LinkedIn and Twitter, where we post this short messages with links to the project activities, so we can follow us. And at this point, I would like to thank you, everyone, physical and online participants, for coming, for sharing, for discussion. If you have any questions, drop me an email. I will connect you with knowledgeable, responsible people, and follow us. Yeah, thank you.